lot of mathematical models. There are only a few that I want to talk about right now because most of them will make a lot more sense as we actually get into it. So for one, reflection. So this is the incident angle. So theta, we've always done this angle. And the incident means the light that is coming in and hits whatever we're talking about. That is the incident light. The R is the reflected light. So the light that goes and hits the mirror, that's the incident, and the light that comes off the mirror, that's the reflected. This is an equation that will be true for mirrors. We'll look at that later. These are true for mirrors and lenses. The equation's on the right. This n here, that's called the index of refraction. And the index of refraction relates the speed of light in vacuum, that's what c is, to the speed of light v inside a material. And remember, the speed of light in a material is always slower than the speed of light in vacuum, which means this thing here is always going to be greater than 1. It's a ratio of speeds, so it has no units. These equations here are going to relate to refraction when we get to materials. Again, I don't want to try and explain it here. It'll be easier later when we're doing examples. And then this lambda naught, remember, is the wavelength of light in vacuum. N is this index of refraction. So the wavelength of light in vacuum divided by n, which remember is always greater than 1, will give you the wavelength of light in the material. And since this number is always greater than 1, this wavelength is always going to be smaller than that one. Frequency doesn't have an equation here. Actually, the frequency of light in vacuum is the same as the frequency of light when it goes into the material. The frequency doesn't change, the speed does, and the wavelength does.